Welcome back, class. Let's move on to page 169. I'm getting a little, okay. Check out our data table here. The table compares the melting points and boiling points of a few molecular compounds and ionic compounds. Use the table to answer the following questions. Ooh, yeah. Methane, here's a formula, CH4, and the melting point is negative 182.4, and the boiling point is pretty low. Rubbing alcohol, formula, pretty low too. Getting a little higher. And water. Whoa, there's a formula, melting point is 0, and the boiling point is 100. I want you to see a pattern. Whoa, water, check it out. It's a small molecule, only 3 atoms. But comparatively, compare it to rubbing alcohol, which is a big molecule. Its boiling point is much higher than rubbing alcohol, and much higher, and its melting point is much higher. Water is special. I'll tell you what, I'll give you bonus points tomorrow if you can tell me on the quiz why water has such a high boiling point. Good luck. Yeah, okay. Graphing. No. Okay, here's zinc chloride. This is an ionic compound. Whoa, its melting point is huge compared to the molecular compounds. Magnesium chloride and sodium chloride, just off the chart. All right, let's keep reading. Poor conductivity. Most molecular compounds do not conduct electric current. No charged particles are available to move, so there is no current. Oh, yeah. Here's another good question. Why? Why is there no electric current in molecular molecules? Well, it's because there's no charged particles to move. Materials such as plastic and rubber are used to insulate wires because these materials are composed of molecular substances. Even as liquids, molecular compounds are poor conductors. Pure water, for example, does not conduct electric current. Neither does table sugar or alcohol when they are dissolved in pure water. Whoa, Mr. Worley, I thought from all the movies I've watched that water is a great conductor of electricity. You know, when the bad guy comes into the bathroom and drops a toaster in the bathtub. Yeah, it's not actually. What's happening is the soap or the bath salts or whatever, that is what's conducting the electricity, not the water. So, if you had pure water and well, don't try it. It's dangerous. Anyway, here's the point. Water doesn't conduct electricity well. Unequal sharing of electrons. Have you ever played tug of war? If you have, you know. Ooh, maybe you should start a new section in your notes. Have you ever played tug of war? If you have, you know that both teams pull with equal force. The contest is a tie. But what if the teams pull on the rope with unequal force? Then the rope moves towards the side of the stronger team. The same is true of electrons in a covalent bond. Atoms of some electrons pull more strongly on shared electrons than do atoms of other elements. As a result, the electrons are pulled more towards one atom, causing the bonded atoms to have a slight electrical charge. These charges are not as strong as the charges on ions. Next page, 170. Polar bonds and nonpolar bonds. The unequal sharing of electrons is enough to make the atom with the stronger pull slightly negative and the atom with the weaker pull slightly positive. A covalent bond in which electrons are shared unequally is called a polar bond. Ooh, yeah. That's another good quiz question. I like it. And also a vocab word. Of course, if two atoms pull equally on the electrons, neither atom becomes charged. A covalent bond in which electrons are shared equally is called a nonpolar bond. Vocab word. Compare the bond in fluorine, F2, with the bond in hydrogen fluoride in figure 17. All right? Here's figure 17. Fluorine. Well, they both pull about the same. But whoa, fluorine on this side is totally greedy. It hogs the electron. It doesn't share any with hydrogen. It's harder to see in this diagram, but it's just really selfish. All right. Polar bonds in molecules. It makes sense that a molecule with nonpolar bonds will itself be nonpolar, but a molecule may contain polar bonds and still be nonpolar overall. In carbon dioxide, the oxygen atoms attract electrons much more strongly than carbon does. So the bonds between oxygen and carbon atoms are polar. But, as you can see in figure 18, a carbon dioxide molecule has a shape like a straight line. So the two oxygen atoms pull with equal strength in opposite directions. In a sense, the attractions cancel out and the molecule is nonpolar. Let's check out figure 18 right here. So here is carbon right here, carbon, and here is oxygen and oxygen. And oxygen pulls a lot harder on electrons than carbon. So negative, positive, negative. But because it's a straight line, there's no one place on the atom that is technically, on the molecule, that is technically more negative or more positive. It's just all kind of the same. But here's water, a different situation. Well, because of the shape, the hydrogens with the positive charge are on one end of the molecule, right around here, and over here is the negative end of the molecule. So it's polar. Polar meaning that one part is negative, the other part is positive. Nonpolar means neither part is more negative or positive than the other. Class, I recognize that this topic, this paragraph, is challenging. You should pause the video, read it again, until you get it. Attraction between molecules. If you could shrink small enough to move among a bunch of water molecules, what would you find? The negatively charged oxygen ends of the polar water molecules attract the positive charge of hydrogen ends nearby the water molecules. These attractions pull water molecules towards each other. In contrast, there is little attraction between nonpolar molecules, such as carbon dioxide molecules. Next page, 171. Okay, the properties of polar and nonpolar compounds. Here we go, next page. The properties of polar and nonpolar compounds differ because of differences in attractions between their molecules. For example, water and vegetable oil don't mix. The molecules in vegetable oil are nonpolar, and the nonpolar molecules have little attraction for polar water molecules. On the other hand, the water molecules are attracted more strongly to one another than to the molecules of oil. Thus, water stays with the water and oil stays with the oil. If you did the discovery activity, you found that adding detergent helped oil and water mix. This is because one end of a detergent molecule has nonpolar covalent bonds. The other end includes an ionic bond. The detergent's nonpolar end mixes easily with the oil. Meanwhile, the charged ionic end is attracted to the polar water molecules, so the detergent is dissolved in water. Nice. Okay, so that concludes our reading for this chapter. Remember that your goal is either, your assignment is either 1 and 2 or the at-home discovery activity. Now, check this out. While we have a few minutes, I just want to do a little bit of explaining on one of these topics about polar and nonpolar molecules. I'm going to draw two molecules here. Here is H, O, H. And we learned, and I'm going to draw another one. Here's an O, here's an H, and here's an H. And I'm going to draw another one over here. Here's an O, and here's an H, and here's an H. Okay? I'm going to draw little purple lines between the O's and the H's to represent single bonds. Nice. Now I'm going to draw a little green line to represent the I'm going to draw with a blue marker the relative charges. So this side is relatively positive, this side is relatively positive, this side is relatively positive. Whoa, no, Mr. Worley, negative. And this side is relatively negative, and so is this side. Positive, positive. Okay, now I'm going to draw a little green circle to represent the attraction between the negative and positives on these molecules. So this side is the oxygen negative side is attracted to the hydrogen positive side. Same here. These attractions are called hydrogen bonding. And that is my clue for the bonus question. All right, we're almost out of time, class. Good luck. Bring your questions to class tomorrow. Be ready for the quiz. We're going to knock it out. Thank you very much. This has been Mr. Worley, Section 5.3, Physical Science, signing off, telling you that God loves you, and so do I.